recently it is okay. Yeah, so this book is titled Cloud-Based Remote Sensing with Google Earth Engine, and it has recently come out, and it is an effort of more than 100 individuals. So different people have written different chapters. I feel that this 1.5 hour session is although might seem extensive, but it is not enough like for covering entire Google Earth Engine. So I'll try to do justice to whatever I can in this time that I have. And so this is a set of if you go here, you can see there are of F1 to F6 sections. So these are the fundamentals, and then A1 to A3. So A3 also has part 1 and part 2. And okay, so they also have some videos that you can go through. Okay, so coming to the Google Earth Engine, I'll just go through the website first of Google Earth Engine. So anybody who is starting with Google Earth Engine, so first thing you do is go and sign up, and you have to submit an application to okay, so let's say I don't have an account on this email ID for Google Earth Engine. So what you'll have to do is you'll have to go and sign up to and fill this form, and you will have to furnish details on why you want an account with Google Earth Engine. Otherwise, you cannot use Earth Engine. And previously they used to accept all the applications, but these days they are quite selective, and I heard of people's accounts not getting approved. And but if you are doing research and if you write a reasonably good justification, they generally give you an account. So Google Earth Engine is basically it's an HPC. It's a cloud based supercomputer which has all, like, almost they are trying to keep all the satellite data sets, all the numerical weather prediction outputs, the ground based observation data sets, and they have this nice website, and in this you can just go and see they have everything is documented really well. So they have, you can even run your own machine learning algorithms on Google Earth Engine. But yeah, again, the thing is that you will be restricted by the bandwidth limitations, so you cannot just abuse the platform, because there are other users as well. and and there are ways to get more bandwidth. You can apply, or you can ask Google to increase your bandwidth. So this is okay. So why was it needed? Like, why did they come up with this kind of a tool? Was because, so for example, there were data sets like so there are these missions like Landsat and Sentinel. Now, handling these data sets previously, so if you would have to deal with the Landsat data, so Landsat is used for a lot of agricultural applications. So what people will do is you would have to go to the NASA GSFC website. You'll have to download the data. You will have to do a lot of pre-processing. You have to go through the manual of, or the technical documentation of each of the product, and then you'll have to perform those pre-processing steps. And then that itself was a huge bottleneck, and it used to take a lot of time for people to come to a stage where they can use the data for their applications. So this was, so every satellite, every mission, every data set will have their own nuances, and based on those customized, or based on the data sets, people would do their analysis. 80-90% of the time it will go in just handling the data. So that is where Google Earth Engine has come out to be really handy. Now, what they have done is they have basically ingested all the satellite. Now, I won't say all, but they are working to include all the data which is which starts coming, or which is new, and which they have not ingested. So they keep that, and then what you just have to do is, so the Google Earth Engine has got JavaScript and Python APIs, so you can just use those APIs. And for example, this is a Landsat 9 data which has started coming, and this is a very recent data. The data set, you can see it's available from 31st of October 2021. So this satellite was launched, I think, sometime last year, and what they would give you is orthorectified, atmospherically corrected products. So you don't have to even do the basic data pre-processing or standardization. And what you can just do is you can just copy their template from here. So this is how you would access the data in Google Earth Engine. And you can just so Python and JavaScript APIs. So this is most commonly used in Google Earth Engine is JavaScript. But now Python community in Google Earth Engine has grown a lot. There is not much difference between Python and JavaScript in when it comes to Earth Engine, because they have written the libraries in such a way that you can very easily translate this code to Python. So for example, you have var dataset equal to ee dot image collection. So this ee is the Earth Engine library. So when you are using Python, you just have to say import Earth Engine as ee. When you are using JavaScript, you can, so for JavaScript they have this thing called as the code editor. Okay, just a second. Okay, so they have you have to go to code.earthengine.google.com. Now when you go here, you should have a working and approved account of Google Earth Engine. So I think I'm already logged into this. I'll show you from another browser, let's say. Okay, so you go to code dot, just give me a moment. Code.earthengine.google.com. Okay, so once you go here, it will ask you for a sign in, and what you have to do is you have to basically sign into an Earth Engine account which is approved. And then what this will give you is this kind of an interface. It's called the code editor for Earth Engine. Now this has
Excuse
got,
me.
yeah.
The demo, what you're saying right now, the log.
Okay, fine. Thanks for letting me know. Yeah, so what I was saying was that so you would go to, let's say I'm going in another browser where I've not logged into to Earth Engine, and so it will ask you for so you have to log in using some account which has been approved for Earth Engine, and then you will get this code editor. Okay, so in this code editor on the left side you can see you have the scripts, docs, assets. So you have the files. Then you can write your JavaScript code here in the script box. And then you have on the right side you have inspector, console, and tasks. Okay, so console is basically if you print anything in the code, if you just give a print statement, it will be printed in a console. Inspector is if you can basically click on the maps to inspect the layers. We'll see more on that. And then in addition to code editor, there is something called as task manager. Okay, so if you just search for Earth Engine task manager. Okay, so yeah, it is code.earthengine.com/tasks. So you can see this Earth Engine task manager. This is something very similar to, so those of you who have worked with large HPCs, and for example in PBS or in Slum, you would do a B jobs, you would do SQ minus U username, which will give you a list of all the jobs running in the background. So you can also run the jobs in background using Google Earth Engine. So, and how to monitor those jobs will be very easily handled by task manager. So you can actually, so this is one job that I submitted I think yesterday, and it will, after, if it is running, it will show you something like something is buffering, and then it will give you this metadata on the details of whether it has completed or not. So these are some brief on Google Earth Engine. Now I will move on to this book that I was talking about. And okay, so this book has I think I'll be able to cover the first fundamental chapter today, which is the most basic thing that you should be aware of if you are working on Google Earth Engine. And okay, so this is on programming and remote sensing basics. So okay, and the author is Ujjwal Gandhi. So he also runs a company which is called Spatial Thoughts. I think I should just mention that. Spatial Thoughts. Yeah, this guy was actually a part of the Google Maps team, and later on he has his own startup called Spatial Thoughts. He used to teach this course on Google Earth Engine for a long time. It was a paid course, and now he has opened up a lot of material for anyone to learn Google Earth Engine. And so this first chapter is basically written by him. And so okay, we'll maybe go through the theory first. So it's a Google Earth Engine is a cloud-based platform for scientific data analysis, provides ready-to-use cloud-hosted data sets and a large pool of servers. So these are like most important keywords you should know for Google Earth Engine. It's hosted on the Google servers, and the data sets are also hosted on the cloud. So you don't have to download any data set. So that's another advantage with Google Earth Engine. This is very useful for people who are working, let's say, in universities which do not have good computational resources. And in that case, for example, if you have to work on long term data sets of satellites, or maybe some reanalysis data sets, you cannot download terabytes or petabytes of data in your system. And if your institute or organization doesn't support that, it's very difficult to do analysis or work on that kind of data. So that is where Google Earth Engine is really helpful for the young researchers. And okay, so this they say that the computations are run fast and ability to use. So this Earth Engine API is the one. It's, you can consider it to be a different language only, although it's like a library in Python and JavaScript. So this is how Earth Engine API is how you would basically communicate with the Earth Engine servers. It allows you to specify what computation you would like to do, and then to how to receive the results. So this is designed so that users do not need to worry about the computation. So you don't need to, as an end user, you don't need to care about how the computation is happening at the back end. You can just work on your own application, whether you are working in hydrology, or you're working in agriculture, or you're working in climate science. You can just use it as if you just have the pre-processed data set, and leave it to the Earth Engine servers to basically do whatever they are doing at the back end. And the users just specify what needs to be done. It greatly simplifies the code by hiding the implementation details from the users, and also makes Earth Engine very approachable for users who are not familiar with writing code. Although JavaScript might be, if those of you who are not familiar with JavaScript, it might sound like something difficult or something which you don't know, but you you will find it easy actually. Earth Engine, the learning curve is much easy. That's the way they have written this API. So as they say, it's language agnostic, and Google provides the official client libraries to use the API from both JavaScript and Python. And this largely remains the same regardless of the programming language you use. And the okay, so JavaScript, yeah, as I was talking about, may not be the first choice of programming language for many researchers and data scientists. And but this book is based on JavaScript because it's the most easiest way to use Earth Engine JavaScript, like to use Earth Engine. And as we were seeing, so it comes with a web-based code editor. We have already seen that. So this is the web-based code editor. I will show you live examples, and that allows you to start the Earth Engine JavaScript API without any installation. You don't need to do any installation. You don't need to call any library. You can just directly use whatever is there in the Earth Engine API. You can directly use without worrying much about the installation or details, and provides additional functionality to display your results on a map. Okay, so this one I did not talk about. This last panel at the bottom, this is the display panel. Okay, so your results, if you are plotting something, if you're plotting on a map, you can basically see that on this in this display panel. And in the console you can also plot maybe line graphs or bar plots, like I've done this. And you can also, this is all interactive, so you can even see how it is looking. Okay, so then it provides an additional functionality to display your results on a map, save your scripts, access documentation, manage tasks, and more. So manage tasks, how would you manage tasks? You would basically go to the Earth Engine Task Manager, and you would see which tasks are running, which are not. And also that's like kind of a personal experience that I have, that the task manager, it's useful in a way that your bandwidth is limited. You can only make a certain number of requests per unit time. So if you run lot of jobs, it will take a long time for your all the jobs to complete. So you have to manage your tasks using the task manager efficiently. And it has a one click mechanism to share your code with other users. Okay, so you can just, for example, you can just go here, and you can just say, go to get link. Okay, so get link, or you can copy script path. You can then get the link, copy it, and you can share this link with any user on Google Earth Engine, and they will be able to just run your code. The condition is they should have a working Google Earth Engine account, and allowing for easy reproducibility and collaboration. In addition, the JavaScript API comes with a user interface library, which allows you to create charts and web-based applications with little effort. So in practice, you don't need to become a JavaScript expert to use Earth Engine. The basic syntax described here should be sufficient. Good tip is that if you find yourself doing something complicated in JavaScript, it might be done much better in Earth Engine. Okay. Okay, so then we will go to getting started with the code editor. So you can at your end just if you go to this book website, you can click on these drop down bars links from this go to book tab, and this will basically lead you to these Google Docs of the book. And so you just you just go to this code.earthengine.google.com, and then there is a repository for this book, and you can add this book to your you can see that I've already added it. So this projects GEDU and Google Earth Engine book. Okay, so the book scripts will then be available in the script manager panel. If you have trouble finding the repo, you can visit this. So there's a link that you can visit for help on accessing the scripts in the Google Earth Engine. Now, the code editor is an integrated development environment for Earth Engine JavaScript API. Offers an easy way to type, debug, run, and manage code. Once you have followed Google's documentation on registering for an Earth Engine account, you should follow documentation to open the code editor. Okay, so you can see that there is this docs here. Okay, so here all the documentation of Google Earth Engine is available. You can just go and visit this anytime, and Okay. Yeah. And search for the documentation of Google Earth Engine. Okay, so we have seen, yeah, this is how it looks like. So the code editor allows you to type JavaScript code, execute it. So how would you, so this is a hello world program. Now to run a hello world here in JavaScript. Okay, so we'll see this. Okay, so this in this script first, okay, so you just print hello world. Now if you have to create a variable, for example, the variable name is city, so you use the var keyword in JavaScript, and we just assign this string to it, and you have to, in JavaScript you have to so every syntax, every line ends with a semicolon. And then let's say we print the city. Okay, I'll go to the book. Okay, so then the output will be displayed on the screen. You can see if you just say print hello world on the console. The console is here. Okay, so on the console, this will print hello world. I'll just run the entire code in one go, and then so you now know where to type the code. So you have to type it here in the code panel, and then you can also save this. So this will be saved in your Google Drive, which is linked to your Google account. Okay, so if this is your first time using the code editor, you will be prompted to create a home folder. This is the folder. So okay, yeah, you can keep all your scripts inside this home folder, and you can also create a Git repository so that whatever codes you run, it gets linked to your GitHub repository, and it's just directly goes there. Now, okay, so we were looking at this Hello World program. Okay, so yeah, okay, yeah. So then the coming to some basics of JavaScript, I'll quickly move from this. So we have seen that the var keyword is used to declare the variable in Earth Engine. So this is how you will create this city variable. Okay, now if you print this, it will print the city in the console. You can also assign you can have a number, and it automatically, so in Earth Engine it API, so it in JavaScript it automatically assigns the data type to the variable based on whatever you are assigning. And then there are also lists in JavaScript. So you can see this. We have this list which is cities, and we'll print this, and then you have objects. So these objects are like dictionaries in Python. You have the key value pairs in these objects, and they start and end with curly braces. And you can see that this syntax, this ends with the semicolon. So it's a good coding practice, and also helps the JavaScript understand what you're trying to say. Okay, so then the object will be printed in the console. Now you can also have functions in which are you have to. So this is JavaScript. So the way to create a function is, so this is the syntax. So we have the greet function, and then this is the function, and greet is the name of the function. Function is a keyword, var is a keyword, and then something that you want to return. Okay. Okay, and how would you comment in Earth Engine? So you have to use these two backslash, or if you want to do multi-line commenting, then you do a control plus. You select all the lines, okay, and do a control plus. Okay, so let's say I just select all these. I press control. Okay, no, this is not working here. I think function plus. Okay, so my system has a function key. I think that's the issue here. But yeah, you would in Windows, control plus on Windows, and command plus on Mac. These will work for commenting multiple lines in one go. Okay, so we have now reached the code checkpoint F10A. I will now run this code here. So you can see that we are printing hello world. So hello world is getting printed in the console. Then the city variable, it's a string variable, which so we are printing it, and we can see that San Francisco is getting printed. You can also assign a number to it, to another variable, which is population. So that is getting printed there. And then we can even have a list. Now if you print the list, it will give you something like this. So you can see here San Francisco, Los Angeles, New York, Atlanta. And then we have the object. Okay, so which is similar to dictionaries in Python. So the object, okay, so you can see that it has got three properties, which is, so the key and value pairs are getting printed. So yeah, that's why this statement print city data. And then we have the greet function. Okay, so return hello plus name. So if you pass a name, so let's say we pass world, it says hello world. We pass readers, it says hello readers. Okay, so then this is a comment and then checkpoint. So this was on the basics of JavaScript. Now coming to the basics of Earth Engine API. So Earth Engine has got so many classes, as you can see, e.algorithms, e.array, blob, classifier, clusterer, confusion matrix, date range, dictionary, error margin, feature collection. Most important are image and image collection. So you would see quite often image and image collection being used if you are working with Google Earth Engine, irrespective of whether you are working in Python or JavaScript API. Now let's learn how to use the API. So let's say you want to add two numbers represented by variables A and B. So this is how you would declare the variable. So you would just say var A equal to 1, var B equal to 2. And so in the previous section, we saw how to store numbers in variables, but not computation. And so you would not write something like var C is equal to A plus B. So that won't work. Now in the Earth Engine API, what you would do is you would use function. The function is so first of all, you would have to you'd have to typecast everything into an Earth Engine data type. Okay, so an Earth Engine number is e.number, okay, with an N capital. And then in the argument, what you have to give is that number which is coming from the as a JavaScript variable. So then to add, you have to use this function called add, and this is agnostic to the programming language. So you will basically do the same thing in Python and JavaScript. So the way to add the two numbers is, so you would say result equal to ee.number A dot add B. Okay. So if now you print the result, this will now print you the, sorry, this will now print you the sum of those two numbers. And so that's what they say. By now you may have realized that when learning to program in Earth Engine, you don't need to deeply learn JavaScript or Python. Instead, there are ways to access the Earth Engine API, and the API is same whether it is called from JavaScript or Python. Now there is another example to drive this point home. Let's say you are working on a task that requires you to create a list of years, or let's say a list of numbers from 1980 to 2020 with a 5-year interval. If you are faced with this task, the first step is to switch to the docs tab and open the list module. Now browse through the functions. Okay, so where was the docs tab? So we have seen that this is the docs tab. You go to the ee.list module there and browse through the functions and see if there is a function that can help you. So you will notice a function ee.list.sequence. So clicking on it will bring you to the documentation of the function. Okay, so let's say we have this e.list.sequence. So the arguments that you have to give are start, end, step, and count. Okay, so let's see its usage. So now let's say you are making this year list. So you will declare it, you'll say var year list equal to e.list.sequence. The start, the end, and the step count is 5. So you will have the year list. So now if you print the year list, it will print you numbers from 1980 to 2020 with a 5-year or with a 5-number step. And you can see that this is not Python, because if it was Python, then 2020 would have been excluded. So this is actually just Earth Engine API. And okay, so this will be visible in the console. And okay, so now we come to this code checkpoint F10B. So let's go there. Okay, yeah. Just keep any questions coming if you have. I'll be happy to take them. Okay, yeah. So you can see that here we have this variable A, then B, and then you can add these two numbers. You can just say e dot number A dot add B and then print result. So it just prints 3. And then you can see here we have the year list. Okay. So then moving on to the next section in this chapter. So exploring images. This is written by Jeff Howarth. So satellite images are at the heart of Google Earth Engine's power. This chapter teaches you how to inspect and visualize data stored in image bands. We first visualize individual bands as separate map layers and then explore a method to visualize 3 different bands in a single composite layer. We compare different kinds of composites for satellite bands that measure electromagnetic radiation in the visible and non-visible spectrum. We then explore images that represent more abstract attributes of locations and create a composite layer to visualize change over time. So the learning outcomes are, now we'll see how to use the code editor to load an image, select the bands. Okay, let's go to that very quickly. Okay, so we to begin with, what you would do is, so you would construct an image within the code editor. So in now Earth Engine module, or the library, that has got a data type which is called image. Okay, and you can access so we were seeing from the, so let's say there is this page of from Earth Engine data catalog for Landsat 9. And you can see when you have to access this the image the data. So it says var dataset equal to e.image collection, and then you have to give this string. Now what is this? This is basically inside the Google Earth Engine cloud, the location where the data is stored. Okay, so Landsat LC09 C02 T1 underscore L2. This is a level 2 data. So that's what they say here. So Landsat. So this is a different data set. This is basically an image. So when you click run, the Earth Engine will load this image captured by the Landsat 5 satellite on June 6, 2000. Okay, so on June 6, 2000, you can see this 0606 2000, and you will not see any output yet. So now you can explore this image in several ways. You can retrieve the metadata. So if you just define an image, okay, and you just print it, it will print the metadata for you. How that looks like is something like this. So you have the image, okay, and then it will show you what is the type, ID, version, what are the bands. So okay, bands is a very important concept in the Earth Engine data. So let's say we go to this data page, and it shows us that this has these bands, the short range band 1, band 2, up to band 7. That's what the bands that Landsat has. Now these bands and the actual bands that are coming from the satellite, they mean the same thing. So they don't mean anything different. But let's say if you want to go to some other data set, let's say you are going to era 5 land. Okay, now you go to this era 5 land hourly, and but so this is a these data sets are basically from the European Center for Medium Range Weather Prediction. Now here there is no concept of band. This is not a satellite data. It's a reanalysis product which is merged satellite plus ground-based observation plus numerical model, and that is also being made available via Google Earth Engine. Now bands here are just variables. So these are the different variables that yeah. So these are the different variables that that are there in the era 5 dataset, which is available from Earth Engine. Okay, so then yeah, so yeah, I've got a message, yeah, saying, so yeah, I will move very quickly to the application in urban studies. So I'll just go to that. I'll show you some applications to that. Let me just first complete the basics so that the audience is clear about these things. Okay, so then to visualize an image, what you would do is you would say map dot add layer, and this will just plot the data, and you can pass the arguments such as the bands, the min, max. So these arguments you can pass here, and you have to give the image that you want to display. Okay, so I will skip all of that. I will just run this one. Okay, so this is your first image that you have, let's say, plotted. Okay, so you can use, so Landsat is very highly used for urban applications, for your agricultural applications, for different hydrological applications. So this is a single image that has been accessed from the Earth Engine. And then, okay, so then there is a point. So what you can do is you can actually just you can go to in the inspector module, inspector tab. You can click here. Okay, and then this gives you, okay, so for the image there are these 19 bands. Okay, so there are three layers. If I just switch off the third layer, so just, let's say we just see the first layer, so you can see the band values. Okay, so what you can do is, for example, there is a flood over a region. You can just go and visualize the data over that region. With the inspector tab, you can see the values, how the land cover is changing over that region. Okay, so then, yeah, so the map function, it has got a lot of different other arguments as well, like bands. You can give what band, so in an image collection, what band to visualize, the min, the max. Okay, and then there is also, you can also set the opacity. So you can, in the background, you can select Google Maps, and then you can set the opacity. So then, yeah, that's something that we have seen. Then there are true color composites. True color composite is nothing but how you would visualize, let's say you are flying on an aircraft, and how you would visualize the surface. So that is the true color composite. And then you can, so that is basically, if you select the correct red, green, and blue, uh, the spectrum from the data. So you can see, for example, in this satellite data, the band 3, band 2, and band 1, they correspond to the RGB. You can also construct a false color composite. Now, the false color composite is something which you cannot see with the eyes, but you can make a combination of the different bands in the satellite image. And so you can see things like, so the false color composite for the same image. So you can see how nicely it is getting, the land is getting separated from the ocean. And okay, so we will, let's maybe just run this script, and you can, so this is another false color composite that is run. So this is the code checkpoint F11B. Okay, let's go here and, yeah, run this. So you can see that while it is running, okay, so here it shows you these tabs. Okay, so then the last one to run was this one, short wave false color. So you can also zoom in through this. Okay, so this is over Shanghai. So the first one is the true color composite. Okay, no, the second, this one is the true color composite. Then this is the first false color composite, and sorry about that. Yeah, so you can see that here we have plotted the different composites from the Landsat, yeah, from the Landsat 5 mission. And then we have okay, I'll just skip this color. Okay, so then coming to one of the urban applications. So one is, you can basically visualize the nighttime lights. Okay, so if you want to see the extent of urbanization, okay, uh, there is this data set which is the nighttime lights data. I'll just go to, okay. So there are two nighttime lights data sets which are available in Earth Engine. So one is the DMSP OLS. Okay. So DMSP OLS is, I think, the older one. So this is, okay, not from 96. So there are, even in Earth Engine data catalog, you will find that different products of the same from the same mission are available. So this is the DMSP OLS nighttime lights data version 4. This is from the Defense Meteorological Program uh, from US. Okay, so from the Colorado School of Mines, and you can see that this is available from 1992 to 2014. So the variables, the bands that they have. So this is at around 927 meters resolution. The bands that you have. So stable lights is what you will use mostly. And then there is, after I think 2013, there is another data set which is available, which is the VIRS nighttime day or night band composite. So this is available from 2012 to present. Okay, so present basically means like whatever, until whatever date they have updated in the Earth Engine cloud. So here you can see that we have the average radiance. So this is from the VIRS satellite, and approximately half a kilometer spatial resolution. So this nighttime lights is nothing but the satellite can see the lights that are coming in the night, and also what they can see is okay, so you can, okay, so you can see these bright spots. These are the cities. Okay, so that's what they say, how bright the earth was. So Pyongyang, for example, in North Korea, you can see that so this is over East Asia. There is darkness, and dense strip of lights over Japan, west coast of Taiwan, and bright spots over Shanghai, large blob over Seoul, over to the north and east. Okay, now let's say you want to see the change. Okay, so let's say you want to see how urbanization has happened. So lights, or the availability to electricity, is a very good index or a parameter for estimating the urbanization. And what you can do is you can maybe compare the how the nighttime lights it looks into the, for example, you can visualize that in the year 2003, 2013, and also in 2000 in 1993. Okay, so what you would do is so let's say we load this 2003 data. Okay, you say e.image. So uh, this is the path, and then you select dot, you do dot select stable lights, because that's the band. If you just do e.image, it selects all the bands, so it just has all the variables. And then you would say dot rename. So you would rename this variable to 2003, and this variable you rename to 2013. Now if you can calculate the so you can add the bands. Okay, so just like in RGB, okay, you can add or superimpose these two bands together, and then when we have to plot it. Okay, so you can just say map dot add layer change image. Now this is where the beauty of it comes. So this code does a few things. First, it creates two new images, each representing different slice of time. And okay, so that's okay. So then it uses the add bands method to create a new 3-band image. Now this it does by taking one image as if so. Lights 13 is the first band, lights 03 is is another band, and lights 93 is the third band. So finally, the code prints metadata to the console, adds layers to the map. So you do this, okay. So now when you do a map dot add layer to that change image where you have three, so the three images that you have are corresponding to 2013, 2003, and 1993. Those are corresponding to RGB, okay. So here wherever you can see the red color, okay, so you can basically read the colors, and you can also use the inspector panel to confirm this. So you can see many clumps of white pixels over urban cores. So why white pixels are coming here is because if you have high values for all the years, for 1993, for 2003, and for 2013, you will have white, because if you just add all the colors in the electromagnetic spectrum, you get a white. Okay, so these are the urban cores. So if you zoom into Shanghai, you will, okay, I will just so this is okay, so you will notice that these white peripheries, these white blobs are regions which are which were urbanized even in 1993, and same in 2003 and 2013. Now, yellow represents locations that were bright in 2013 and 2003, but were dark in 1993. So around this white, you can see these yellowish tinges. Okay, so basically the development started sometime after 2003. So that is what yellow represents, and red represents locations that appear bright in 2013 but dark in 2003 and 1993. So you can see these reddish regions which are, so it's how a city basically you can consider a city to be like a living organism, and it'll start from, let's say, the city center. It just keeps expanding, and the outer regions, you can see that there are reddish tinges which represent regions that were bright in 2013. So there were a lot of lights, but not in 2003 and 1993. Now uh, okay, so yeah, that's fine. And in addition to this urban change, this also shows the changes in the resource extraction. So these nighttime lights, not only they represent the so the satellite will just capture the lights, right? And it not just captures the lights. It you can also see geographic shifts of fishing fleets. You can also see the mining activities. Okay, for example, this is over US. Okay, so you can see this red blob. So red blob basically means that it was bright in 2013, and this represents the fossil fuel extraction that through gas flaring. So gas flaring also releases a lot of light. Okay, so this red blobs that you can see somewhere near Alberta, south of Texas. These are regions which correspond to gas flaring in Alberta, North Dakota, and southeastern Texas. And so if you pan to Persian Gulf, okay, so you can see where oil is getting extracted. You can see where fishing is being done. You can okay, so this one is another image from the Middle East. So you can see that we have a blue here. So this blue, it corresponds to regions in so near Syria, near the border with Iraq, signify the abandonment of oil fields after 1993. So blue basically represents region which was bright in 1993 but which became dark later on. So because of the situation there, the oil fields got abandoned around that region. Okay, so you can see that it is also very nicely it is visible in this nighttime lights image. Okay, so then we finish this here, and okay, so I will quickly move on to the raster data sets. which is the next section. Maybe I can run the okay, the last one of the last notebooks, the scripts. Okay, now this is the Landsat. All these are land. Okay, anyways, in the benefit of time, I will just go through the book. In the end, I will show you an index which is really good. It's called normalized difference urban index. Okay, so yeah, I'll just go through this section now. So you just like an image, we have another data type in Earth Engine. It's called the image collection. So how you would access an image collection is you would just say up until this. So if you remember, when we were selecting an image, we were explicitly giving the path of the image. But image collection is like you are giving a path to a folder which contains a lot of images. So sorry this is the let's say you select the Landsat 8 image collection. Yeah. So and then you can first of all print the size, which will give you the number of images which are there in this image collection, and then you can just plot it over. So you can see that it plots so many images for you. And this print on the console, wherein it says it has got 12760, around more than 1 million images. These are the images which are being used in this image collection. So to basically plot this, so all these images are in that image collection, and you are just plotting the image collection directly. Okay, so this is the code checkpoint F12A, F12A. Okay, this is the one. And let us run this. So, yeah. Okay, so if we run this, it's taking time. Okay, I'll just move on. Yeah, so what you can do is with an image collection is you can filter with dates. Okay, so you can use the filter date function. You can filter with dates. You can basically select filter by location. So for filter by location, you have this filter bounds. So for that, you have to create an Earth Engine geometry point. You can create a point, polygon, or a region. Okay, it can be any geometry. You have to just give the longitude and the latitude. Okay, so you can just say Landsat winter dot filter bounds, and this will you can print the size of the image collection. You can plot the image collection. Okay, so this one is okay. And then there is another function called first. If you just run this function dot first on an image collection, it will return you the first image. So it has got so many images. The first image of the image collection it will give you. Okay, so then collection of so these images, yeah, just skip. So we have seen filter date, filter bounds, and first. And you can anytime just print this image that you have developed from the image collection, and it will give you the metadata. Okay, so yeah, then there are these pre-made composites. Okay, so you can make some composite. Let's say you combine some of the bands in the satellite imagery. from that you have accessed from Google Earth Engine, but you can also have we also have these pre-made composites from the missions such as MODIS, Landsat, Sentinel, and there are for the climate information, forest or vegetation information. And so the first thing is MODIS daily true color imagery. Okay, so the visible, so they are available at 500 meters and 250-meter spatial resolution. And let us see this code. So you first, let's say, select the MODIS daily data. Okay, so this is an image collection. You are getting the data from here, and then you filter by date. Okay, so you just select this particular date. Now this, since this is a daily data, it will give you a single image. And then because this is an image collection, so it has got so many bands. So now you say that we want to plot these three bands. It will plot in the as RGB, and you can give the min and the max arguments. And then we say map dot add layer. Mode is daily recent. Okay, so this is the variable you want to plot. Mode is vis. This is the visualization object, and then what is the name of the image. So when you plot this, it looks something like this, which is coming from Modis daily true color image. If you zoom over this, let's say this is over Denver in Colorado, you can see that there are gaps in the Modis daily true color image. Now the next thing is which is a pre-made composite is Modis monthly burned areas. So some of these bands are useful. So for understanding where, let's say, there is a forest fire, or there is a fire in a city. So how the satellite can capture that? That is that. For that, this is the variable. So Modis monthly burned areas is a product that you can use. For that, you just have to get this Modis monthly data from this image collection, and then the recent one. So this is, I think, at the time when they were writing this chapter, and then you can just plot this burnt areas. Okay, so this is how your Modis monthly burn image over California looks. Now this is very important because forest fires are becoming a big problem in California, in British Columbia, even over India, because of the impending global warming and climate change. There is more heat, and because rainfall patterns are also changing, so it's more of like concentrated or localized extreme precipitation. So because lot these regions, the western United States, that's going into a long-term drought. So if the soil is not moist, it is dry, there is a lot of heat, it gives a higher chance or probability for the fires. So to understand or to assess where the fires are happening is very important for the uh, regional studies. Okay, so yeah, this is the code checkpoint F12D. I will just see if I can run that. Okay, so this is not synchronous with, yeah. Okay, so then there are other satellite products. So one of them is methane. Now methane is very important because methane is more dangerous greenhouse gas as when it comes to global warming, and has 27 times more global warming potential as compared to carbon dioxide. So 27 molecules of carbon dioxide is equivalent to one molecule of methane. And people have used Google Earth Engine to study, for example, regions, for example, waste dumps, okay, which were releasing a lot of methane in the atmosphere. And then corrective actions were taken to ensure that methane doesn't come out of those waste dumps. And this is available from the European Space Agency satellite mission called Sentinel-5. Okay. So you can access it as so the methane, you can access it from the Copernicus S5P, stands for the Sentinel 5P. And then there are two products which are available. One is the offline, then you have the near real time. Offline is after they collect it, they pass it to some pre-processing and quality control. And then this is a level 3 methane data which is available. Okay, so then you select the band, which is the methane CH4 column volume mixing ratio, dry air, okay, and you filter with date. So from 28th of November 2018 to 29th of November 2018, and you select the first image. And then you can specify the palette in the visualization object, the min max, and you can say where to center the object. You can specify the zooming. Okay, so this is the zooming, how much you want to zoom the map. And then map.add layer, it will just plot this variable with these visualization parameters and name it methane. Okay, so here you can see that for that 28th of November, this Sentinel 5P is getting the data over Africa. So this must be the swath over which the satellite must have flown. And you can see that over Algeria, Western Sahara, over Namibia, South Africa, these are the methane levels. And methane also gets emitted by farming or by agricultural activities, by livestock. So cows are a big source of methane. So uh, the satellite can help us in studying where the emissions are high, and maybe control it, or we can either mitigate or adapt to the climate change. So then comes the weather and climate data, which is very useful for the urban and regional studies again. And so the most frequently used data is the European Center for Medium Range Weather Forecast reanalysis era 5. And as I was talking about, so many different variables like 2 meter temperature, precipitation, they are available. So you can see that this is the ERA 5 maximum monthly temperature for January 2018, which is plotted here. And then we have the land use, land cover, which is very very useful. Like so, uh, so one is the European Space Agency world cover dataset. So they have classified this the on into 11 different land cover classes. The classes are built up, cropland, open water, mangroves. So you can access this data. So this is the ESA world cover map. I think they have not mentioned about one very important data which recently got released. It's called the dynamic world. So dynamic world is 10-meter near real time land cover dataset, which is based on the Sentinel satellites, and it is developed by hand labeling and making a supervised learning data set, and very useful for urban studies. For basically, let's say, I will just maybe show you something. So I so I had actually analyzed or seen this dynamic world data. This came out, I think, sometime last year, uh, and it's a joint collaboration by Google and World Resources Institute. And this data is openly available on Google Earth Engine from 2015 to present. You can see that it's available until 23rd of November 2022. So I will just show you one example that I worked on, or I just was exploring this data set. So this is a dam in Kerala. So there were these Kerala floods in 2018, and you can see that in the base map. This is the in the base map is the actual extent of the dam. So you can see, this is the actual extent of the dam. And then what dynamic world is showing us for that period in 2018, this is the water mask. So you can see that for flood studies, or for understanding, or for first of all, for any kind of study you would need the data. So where the data will come from, now that is a big challenge. And in such events, when we have the disaster strike us, people will first go and save their lives rather than collect data sets, or your ground station data sets, the observatories, maybe they might also get damaged, but satellites will are providing us with a really good source of analyzing such events. So you can see that this is the water mask, and actually this is the extent of this this is, I think, Chulliyar Dam in Kerala. So it's almost overflowing by, you can see the water extent is almost double. So that is what. And this dynamic world is really good, like one, like is the best in the land use, land cover classification data sets. People before these data sets were available, they used to hand label and generate land use, land cover over their region of interest. And also for, like, let's say this ESA, the European Space Agency, this data, it is available for the year 2020 one. But if you want to see how the changes in land use, land cover are happening, that those things are not possible for example ESA land cover, ESA data, or the global forest change. So global forest change, it gives you the difference between 2000 and 2020, and shows you how the forests have changed between between these 2 years. But this dynamic world data, this is so based on Sentinel. So Sentinel, every 6 to 7 days, it has a pass over the same region. So every 6 to 7 days, you will get a new, maybe if the land use, land cover is changing, you will get that particular information. So that is how it is useful. And then there are other data sets like global grid population data set. So you can see that this is available from also available from the Google Earth Engine. So you can plot the in a similar way. For example, this is available for the year 2000, and so most populated regions, and the yeah. So you can do your urban and regional studies. Then we have the digital elevation models. So these are basically using airborne and satellite instruments to estimate the elevation at each location on Earth. So different DEMs are available on Google Earth Engine, and so one of them is the NASA DEM, which for example has been plotted here. And okay, so that was all about those data sets. And then some of the remote sensing vocabulary that okay, I'll just skip these things because I want to show you the normalized reference urban index. Yeah, what you can also do is you can also plot the time series in Google Earth Engine. So you can, let's say, select a region of interest. Okay, I'll just maybe go through this one. Okay, so let's say we want to see how the Landsat is changing. Landsat is, for example, 5 is available at every 16 days over the same region, and you will use this function. So just remember this one, ui.chart.image.series. What you have to give here is an image collection. Okay, and you select the variable from here, filter with dates, and then you give the region as well. So the point over which you want to plot the time series. Now you can see that this time series, it will be plotted in the console in the Earth Engine code editor. And this is for the Sentinel. So you can see every 6 days you are getting a data point. You can do a very localized or analysis, for example, over a grid point. You want to see whether something is changing or from Landsat or Sentinel. So you can do this kind of time series analysis. Okay, and yeah, so that's all about this chapter 1. So I've covered this chapter 1 from this book. I don't think I have the time to cover other chapters. I will show you one example. Uh, so this index is called normalized difference. Yeah, normalized difference urban index. Okay, so this one is available from. Okay, there is an MDBI remote sensing paper which is having. If you have any questions, you can ask them now. Yeah. So what these guys did was, and so the director of one of the director of Google Earth Engine, Rebecca Moore. I think it's this paper. Maybe she's one of the author in this. This paper. So she's an author. She's one of the author in this paper. And this data set. So they published this paper in 2015, building a better urban picture combining day and night remote sensing image. So what they have basically done is they have combined the normalized difference vegetation index NDVI and the nighttime lights imagery to come up with an index at 30-meter spatial resolution, which they call as the normalized difference urban index. Okay, so yeah, there is a whole big you can just go and read this paper. And this is, I think, so they have mentioned everything that they have done to identify the urban regions from the nighttime lights data and from the NDVI Landsat 7 NDVI. Now I will just go to my. I'll run one example for this normalized difference urban index, and I will finish this session. Yeah. So this is I've written this in Python, and so you can see, like, I'm importing the Earth Engine library. I'm saying import folium. Okay, so yeah. Okay, so let me connect to my Google Drive. Uh, okay, so you see this when you do this import, when you do this import EE. Okay, so you have to first run EE.authenticate and then EE.initialize, and this will give you this link. So every time you have to then go to this link and generate a token. So this account is associated with Google Earth Engine, so I will just say continue, and then I will just take these two options, and again I will say continue,
Yeah,
and
Manmeet, can
then
you please
here we
speak a
have,
little bit louder?
yeah, am I audible?
Yeah, now.
I'm audible now.
Yes, yes.
Okay, fine. So yeah, so I will now paste this code here and just run some basic installation commands here, and yeah, so these are the nighttime lights data set which we have. So these were basically a set of 15 or 16 different satellites that were in orbit all over the earth. This is from the DMSP OLS data, and then so there is a paper which shows how to do corrections, some pre-processing to this nighttime lights data, and then we take the Landsat 7 product and compute the NDBI from there, and that NDBI we fuse the NDBI with the nighttime lights to then come out with this NDUI product. Okay, so this is corresponding to the year 2012. Now I will just do a visualization of NDUI, which is corresponding to the year 2012. I will also open Google Maps maybe, and so we can see side by side how what our NDUI is saying, and how the satellite actually say. What does the satellite say? Okay, so yeah, we have the satellite here, and okay, so the NDUI is you can see that it is getting loaded. So these uh, these blobs, these gray color blobs, you can see these are this is what we are getting. I will I will plot this over India. Do you want me to show a particular region? Uh, is there a particular region of interest to the audience? Hello.
Yeah, you can show us Pune because
Yeah. Which one?
Pune. Right now you are residing. Pune, Maharashtra, India.
Yeah, I was not able to hear you properly. So which region did you say?
Yeah, Pune, Maharashtra.
Okay, fine. Yeah. Okay, so let's say this is Pune, and okay, so I will just maybe zoom over the satellite imagery. Let's see something. Okay, let's keep it open like this. Okay, and I will zoom over this NDUI. Okay, you said Pune, right? Okay, so we have this area which is, let's say, it's called Swargate. So this is at 30-meter spatial resolution, and so let's say we okay, let's say there is this region, Jawaharlal Nehru Cricket Stadium. Okay, so we go here. Cricket Stadium, Pune. Okay, so here you can see that right now, so we have a cricket stadium here. So this is not an urban region. So the colors which are corresponding to purple, they are non-urban, okay, and which are red and yellow and green. So red is most urban, okay. So here you can see that this which is the Jawaharlal Nehru Cricket Stadium, and this nighttime light, this NDY is from 2012 that I am having, but this satellite imagery is the recent one. So this is the cricket stadium. Now around that you can see there are these stands, okay. So that is being captured here. So this is being captured, and then we have this street here, okay. So this street which is getting nicely captured, and then there is a lot of there is a lot of vegetation around, okay. So for that as well, so you can see there are these purple blobs, okay. And then there is this Peshwe Udyan. So I think this is and Saras Bog. So this is a park, okay. So yeah, so this is the park, okay. This is that park region you can see here, and which is very nicely, you can see that it is classifying this entire region as purple. Now moving ahead, on the west of it, so there is this something, okay, some Tanaji one, some path is, so this all region to the west of this park, it shows as urban. Let's see what is there. Okay, so you can see that this one in the on the left of this, there are these buildings and these societies, okay, to the left of it. And then we have okay, so then this region, okay, which is, I think, yeah, this one, which is highly populated, looks like highly urbanized, okay. Yeah, this one, this blob, you can see it's coming nicely here. So yeah, the point is that yeah, and then you have the river here, which is also non-urban. So the river, okay, where is the river? Yeah, so this is the river, okay, which our algorithm is classifying as non-urban. So this data, which is the normalized difference urban index, it's a state-of-the-art data set for identifying urban areas, classifying urban regions, and you can exactly at 30-meter spatial resolution. So for example, you can see there is a hospital here. It shows high urbanization over that region, which is, I think, here. Yeah, so you can see this is the hospital, and wherever there is vegetation or there is a river, it decreases. Over the other regions, there is where there is high urbanization, it just shows you high values of normalized difference urban index. So with that, I would like to end this session, and I would like to thank the organizers and the participants for being a part of this session. I think like it takes like Google Earth Engine, if we want to cover completely, it might take like 6 to 7 of such sessions, and completing this book in whole only can give you a very detailed and in-depth insight into what are the potential capabilities of Google Earth Engine. So with that, I thank everyone, and I am happy to take any questions if they are. Now, this lidar is actually on board the International Space Station, and the mission of this lidar is to estimate the canopy heights, okay, the crop height or the forest height, the height of the plant or the tree. And so what you're saying is like we have to basically create that data set. Now there are different studies. So this is how the ZI based lidar data, with that you can estimate the crop height. Okay, so in this study, what they have done is they have used the Jedi and Sentinel-2 for mapping tall and short crops. So basically, they say that the maize crop, it has got a different height. Okay, the height of the maize crop is different as compared to wheat, rice, and sorghum, soybean. And they identify what they do is they basically develop a supervised learning data set, and then they are able to classify and develop this over US, France, and I think China, and develop these crop classification maps. Just maybe I can, yeah. So they first generate these labels, okay, and then they, okay, sorry, and then they basically develop this algorithm to identify maize from the sentinel and satellite imagery use and ZI. And ZI is actually openly available on Google Earth Engine. So the point that I'm trying to put across is, so ZI, otherwise actually processing ZI itself is a big task. So ZI data started coming somewhere around 2018 from on Google Earth Engine. It's available from 2019, and so you can write your own things for your region of interest. So you can see that for China, France, and US, all the yellow regions are maize, and the rest are other crops. So what you can do is, like, if you can so for different crops you can use the color. So you can assume that different crops, it will get captured in the different hyperspectral bands, and then develop a supervised learning data set, wherein you go and you have to hand label the crop information on the ground, and then get the satellite data as an input, develop a machine learning model, and which can tell you what crops are there. Or you can use something like this, which is an indirect way of estimating the maize crops. So in this study, what they did was they developed the model over China and I think France. I don't know France, but they did not use the US data for developing the model. In the US was only used for prediction. So you can see the ground truth in C and the prediction in F. It's matching like 1 to 1. So those are kind of my thoughts on crops. Did I answer your question?